Things that I'm going to present is as follows: introduction, experimental, result and discussion, and finally I will make a conclusion. First, let me talk about the introduction of my research. Friction and wear are very frequent phenomena in our daily life. Friction and wear produce energy waste, material loss, and shorter lifespan of machines. So we need lubrication in order to reduce friction and wear in operating machinery. By the report, one-third of the automobile fuel energy is used to overcome the friction during driving. As you can see in this figure, the old Egyptians also sprayed lubricating oils in the moving route of huge statues. This explains the old history of lubrication in a human history. The three keywords of friction, wear, and lubrication are the three kinds of elements in tribology. Tribology is first used in the research paper of Peter Jost in 1966. It is originated from the old Greek letter tribos, when means rub, and logi, which means study. Tribology is the science and engineering of interacting surfaces in relative motion. It includes the study and the application of friction, wear, and lubrication. Tribology is an interdisciplinary study among chemistry, physics, material engineering, and mechanical engineering. As you know, lubricant consists of 95% of base oil, and which is actually acting lubrication, and 5% of additives, which enhance a function of base oil. Even though the small amount of additives is added, it influences a lot to the function of lubricants. In the past, layer structured materials such as tungsten disulfide, moly disulfide, hexagonal boronitride, and graphite have been used as solid lubricants. But these inorganic materials do not show a good dispersibility in organic liquid lubricants. For that reason, a very thin single-layered two-dimensional material, graphene, which is discovered in 2004, has been attractive in the field of lubrication. Let me talk about graphene a little bit. Graphene is a combination word of graphite and ENE, which means double bond in covalent materials. Graphene is a material which shows characteristics of strong mechanical strength, high thermal conductivity, and thermal properties. Let me talk about graphene oxide a little bit more. The shape of graphene oxide has a large number of oxygen functional groups attached on graphene sheets. So it is difficult to apply in hydrophobic organic solvents. In order to solve this dispersion problem, many attempts have been made to transform graphene into covalent bonds or non-covalent bonds. Functionalization of graphene oxide. In this study, we functionalized the graphene oxide with the various alkyl chlorides by the next two step reactions. The starting materials are graphene oxide and ethylene diamine. The first step is amide bond formation between carboxyl group and amine group of ethylene diamine. The second step is nucleophilic substitution reaction of alkyl chloride to aminized graphene oxide. This figure shows the structure of tungsten disulfide and inorganic fullerene like tungsten disulfide. WS2 has two-dimensional layer structure consisting of tungsten and sulfur. This material shows excellent anti-oxidation property and pressure resistivity and low friction coefficient of 0.03. This material is also applicable to 270 to 650 degree at atmospheric pressure. IF-WS2 has a shape of 2D WS2 sheets piled up like an onion. When this is mixed with functionalized graphene oxides, it acts as a ball bearing between graphene sheets. Gelator, MOB, was also added for dispersion stability. This is experimental part. In order to synthesize functionalized graphene oxide, we have used graphene oxide solution, ethylene diamine, and alkyl chlorides, 6 kinds of alkyl chlorides. We have also used octadecylamine, toluene 2,4-diisocyanate, toluene, and chlorobenzene. We also employed PaO4 base oil and IF-WS2 solution. The first step of functionalization of graphene oxide is the preparation of aminized graphene oxide. Graphene oxide and ethylene diamine are mixed together and refluxed at 75 degrees for 24 hours. Then the product was filtered by PTFE filter with 2 microns of pore size. Finally, the product was dried at 60 degrees for 24 hours to get aminized graphene oxide. The second step is the alkylation of aminized graphene oxide. Aminized graphene oxide is mixed with 6 kinds of alkyl chloride, which are butyl chloride, octyl chloride, and tetradecyl chloride, etc. These mixtures are refluxed at 80 degrees for 24 hours and filtered by PTFE filter with 2 microns of pore size, and then dried out at 60 degrees for 24 hours to get 60 degrees for 20 hours. Finally, we have obtained FGO4, FGO6, FGO8, FGO10, FGO12, and FGO14 as products. This is a dispersion stability test. Functionalized graphene oxide with different size of alkyl chains are dispersed in base oil. PaO4 is used as a base oil. The concentration of IF-WS2 in base oil are varied to 0.1 weight%, 1 weight%, and 2 weight%. We have also applied 0.1 weight% of FGO and 1 weight% of MOB. These mixtures are then ultrasonicated for an hour and left for 30 days. Then we carried out tribological tests with this high-frequency friction wear tester. Each of FGO dispersed PaO oil was applied in between steel ball and steel disc with reciprocating ball-on-disc mode. 10 Hz of reciprocation frequency was applied with 50 Newton of load for 360 seconds. We have also performed 4 ball tests like this. These are the analysis techniques that we have used in characterizing samples. FTIR is used to identify the functional groups of FGO. XPS is used to analyze the binding energies of elements of samples. X-ray diffraction and Raman spectroscopy are used to analyze the crystal structures of the samples. SAM and TEM are used to analyze the morphology and microstructures of the samples. The tribological characteristics are investigated by high-friction wear tester. Let me talk about results and discussions. This is a series of images which is taken from graphene oxide and functionalized graphene samples. GO shows a flat sheet with smooth surface. FGO show crumbled sheets with some folded area due to the introduction of alkyl chains. It shows more crumbled and rougher surface of FGO with the longer alkyl chains. This is the same elemental mapping images and EDS results of graphene oxide and FGO14 samples. As you can see in these images, we observed carbon, oxygen, and nitrogen in the aminized graphene oxide. This is 10 images taken for the samples of FGO4 and FGO14 and IF-WS2. We can see piled up layer structure. of inorganic fullerene like WS2 like an onion. This is a series of FTIR spectra taken for the graphene oxide, functionalized graphene oxide, and aminized graphene oxide. As you can see in the spectrum of GO, absorption peaks of hydroxyl groups are appeared in the range of 3244 to 3777 wave numbers, and absorption peaks of carboxyl group is appeared at 1725 centimeters wave numbers. We can also see absorption peaks of epoxide group in the range of 1042 to 1113 wave number. In FGO sample, methyl groups are appeared at 761 wave number and 2831 to 2978 wave number, and the characteristic peak of amine group is appeared at 1581 wave number. Since peak intensities of hydroxyl, carboxyl, and epoxide groups in GO are decreased, and peak intensities of amine group in FGOs is increased, so we can assume that amine group is successfully introduced to GO sheets. This is a series of XPS spectra which is taken for graphene oxide, functionalized graphene oxide samples. In this survey spectra for 8 samples, oxygen 1s peak is appeared at 532 electron volt, and C1s peak is appeared at 287 electron volt in GO samples, but intensities of these peaks are much decreased in FGO samples, and also N1s peak, which has not been observed in GO sample, is appeared at 399 electron volt. Therefore, we can know amine group is successfully attached to the graphene oxide sheets. These results are also confirmed in the following hyperfine structure B, C, D, E, and F. These are the series of XRD patterns taken for graphene oxide and functionalized graphene oxide samples. You can see the characteristic peaks at 2 zeta values from 23.2 to 23.8 for FGO samples. These 2 zeta values get close to the diffraction peak of graphite. This means disordered graphene nanosheets are rearranged due to the reduction of the oxygen functional groups. As you can see in the table, these spacing values are increased in the order of graphite, graphene oxide, functionalized graphene oxide due to the oxygen group of graphene oxide and alkyl change attached to the FGO samples. This is the test result for dispersion stability. After sonication to the mixed systems for an hour, FGO samples are all dispersed. Even though the GO was not dispersed due to its hydrophilic property. But after 30 days storage, only FGO14 showed a very stable dispersion stability. This is due to the introduction of lipophilicity to graphene oxide. This is also due to the high specific surface area of FGOs like crumbled paper. It revealed that van der Waals interaction between the tetradecyl chains of the FGO14 and the alkyl chain of PA of oil gives a long-term dispersion stability. This is the tribological test result for PAO and FGO samples. Compared to the friction coefficient of PAO base oil, the friction coefficient of PaO4 with 1% IF-WS2 sample and PaO4 with 0.1 weight% FGO6 and 1 weight% IF-WS2, and the sample PaO with 0.1 weight% FGO6 and 1 weight% IF-WS2 and 1.0 weight% MOB sample were decreased. D sample showed the best result, decreased by 13.6 in FGO samples compared to the PaO4 base oil. Compared to this value, this D data was much decreased in coefficients. The reason why FGO14 showed a superior tribological characteristics is based on the dispersion stability due to alkyl-functionalized graphene oxide and the synergistic effect with WS2. This is a wear track test result for PaO and FGO samples. As you can see in this wear track pattern, compared to the wear track data tested to the PaO only, the test result for FGO samples with tungsten disulfide additive showed decreased value in wear track. As a result, this sample, PaO4 with 0.18% FGO6 and 1.8% IF-WS2 and 1.8% MOB, this sample showed the best performance in reducing wear track by 21.18%. That's great value. Figure 15 shows the temp image of lubricant sample after finished the friction test. In this figure, you can see the temp image displays IF-WS2 inside and the FGO sheet is wrapped around IF-WS2. This result indicates that IF-WS2 acts as a ball bearing between FGO sheets. Figure 16 shows the lubrication mechanism of FGO, IF-WS2, and MOB. This figure suggests that the wear track in the contact surface was filled with IF-WS2, and IF-WS2 was introduced between FGO sheets, thereby serving as ball bearing, resulting in lubrication. In addition, gelator, MOB, fixed the additives of FGO and IF-WS2 to prevent agglomeration and sedimentation, and eventually maintain dispersion of these additives. Let me make a conclusion for the seminar. We have prepared alkyl-functionalized graphene oxide nanosheets for oil-based lubricant additives by using 6 types of alkyl chlorides. FTIR and XP spectra show a decrease in the often oxygen functional groups of the GO, and the appearance of CO bonds reveals the successful introduction of long alkyl chains of GO. XRD and the Raman spectra show the wider interlayer spacing and the formation of amorphous carbon of disordered sp in FGOs. By the dispersion stability test, the FGO14 showed a very stable dispersion stability during 30 days due to the introduction of lipophilicity to the graphene oxide in PaO4 base oil. And the van der Waals interactions between the tetradecyl chain of FGO14 and the alkyl chain of the lubricant have provided long-term stable dispersion in the lubricating oil. Tribological test. By this test, this sample, PaO4 with 0.1% FGO6 and 1% IF-WS2 and 1% MOB system. This system shows the best performance. This material reduced the friction coefficient by 13.06%. This material also reduced the width of wear track by 21.818%. Therefore, we observed alkyl chain length in FGOs directly influences to the dispersion stability and tribological characteristics of PaO oil. Finally, we observed additional inorganic fullerene-like tungsten disulfide acts as a ball bearing between FGO sheets and show the synergistic effect in tribological functions.